Welcome to Talk Tensors. If you are listening to this, you are likely obsessed with the same thing we are. The rapidly evolving frontier of machine learning, the mathematics of intelligence, and that nagging question of whether the ghost in the machine is actually thinking or, just pretending to. I'm your host, the one asking the questions you're screaming at your dashboard.
And I'm here to help navigate the noise and find the signal in the research.
Today, we are doing a deep dive. And I don't mean we're just reading the abstract. We are cracking open the hood of a paper that I honestly believe represents a massive pivot point in the history of large language models.
I agree.
We are looking at the seminal work from OpenAI authored by Hunter Lightman, Vineet Kosaraju, and their team titled Let's Verify Step by Step.
This is a crucial one. It really is. It's one of those papers that people cite constantly, but few have actually sat down and, really digested the mechanics of.
Yeah.
It tackles what is arguably the most persistent, annoying, and frankly, dangerous problem in AI.
Which is the hallucination of logic. Right. We're used to the model hallucinating facts. You ask for a biography of a fake person, and it invents this beautiful life story. That's kind of funny.
Right, that's a party trick.
But what's trickier and what this paper really focuses on is when they hallucinate reasoning.
Yes, the confident idiot problem, as it's sometimes called.
Yes, oh my God, yes. They give you the right answer, but the steps they took to get there are absolute nonsense. Or worse, they give you a wrong answer, but the logic sounds so incredibly academic and confident that you just nod along and, build your bridge using those numbers.
And that is the core tension here. As models get larger, as we move from GPT-3 to 4 and beyond, they get better at reasoning, yes. But they also get significantly better at deception.
They get better at lying.
In a sense, yes. They get better at producing convincing-sounding falsehoods. So the central question this paper asks is, how do we teach a model to not just output the correct final string of text, but to actually adhere to correct logic? How do we verify the process, not just the outcome?
And that leads us to the main event, the title fight. In the blue corner, we have the reigning champion of machine learning reinforcement, outcome supervision.
Right.
And in the red corner, the challenger, process supervision.
That is the thesis statement right there. Historically, we have relied almost exclusively on outcome supervision. That means you give the model a task, it spits out an answer, and you give it a cookie if the answer is right.
Thumbs up, thumbs down.
Pretty much. This paper argues, with some very strong evidence, that outcome supervision is just insufficient for complex reasoning. It's too noisy. Instead, process supervision, where we reward every single step of the chain of thought, is the future.
But here is the kicker, and this is the thing that made me stop and reread the abstract like 3 times. Usually in AI safety, we talk about the alignment tax.
Right, the old pessimistic assumption. It's been with us for years.
The idea that if you want to make a model safer or more honest or more interpretable, you have to pay a price.
A price in performance.
Yeah, you have to make it a little dumber, a little more constrained, or a little slower to make it safe.
That has been the prevailing wisdom for a long time. Safety is a brake pedal. It slows you down.
But this paper says, no, it says that's wrong.
Correct. This paper suggests that process supervision effectively eliminates that tax. In fact, they argue it incurs a negative alignment tax.
A negative tax, so a rebate.
Exactly. By making the model safer, by sourcing it to be honest step by step, you actually make it smarter. You make it more capable at math. The safer model is the stronger model.
That is the holy grail. That's everything. If safety equals capability, then we don't have to fight the labs to implement it. They'll just do it.
They'll do it because they want the performance gains.
The incentives are aligned.
Precisely. It aligns the incentives of the engineers with the incentives of the safety researchers. It's a huge deal.
Okay, let's unpack the machinery here. We need to understand how they proved this, because this wasn't some, small experiment run on a MacBook. This was OpenAI throwing serious compute at the problem.
It was a very large-scale investigation. And to test reasoning, they couldn't just use simple conversational prompts. They couldn't use, write me a poem about a cat.
No, you need a ground truth.
You need a ground truth. So they went straight for the hard stuff. Mathematics. Specifically, the math data set.
I want to pause on the data set for a second, because I think some listeners might hear math data set and think of like GSM 8K, the grade school math 8K, which is usually the benchmark.
Right. Johnny has 5 apples, he eats 2.
Exactly.
No, this is much harder. GSM 8K is great, but modern models are, they're starting to saturate it. They find it too easy. The math data set is composed of 12,500 problems from high school math competitions.
Wait, like the math Olympics kind of stuff?
We're talking AMY, AMC 10, AMC 12, algebra, calculus, number theory, probability.
Yeah.
Really complex problems.
So these are problems designed to trick smart humans.
Exactly. They require complex, multi-step derivation. And crucially, if you make one small logic error in step 3, the answer you get in step 10 is going to be total garbage. It's a very fragile chain.
Okay, so they have this incredibly hard data set. What is the engine under the hood? What model are they actually training here?
They are operating with models that are fine-tuned from GPT-4. So we are dealing with a state-of-the-art base model for the time. But, and this is a detail that I think is often missed, they did something interesting before they even started the supervision experiment.
Oh.
They did a round of what they call lightweight pre-training on something called Math Mix.
Math Mix. Sounds like a terrible trail mix you'd buy at a university bookstore. What is it?
It's a data set of roughly 1.5 billion math-relevant tokens.
1.5 billion.
Yes. They took the base GPT-4 and essentially fine-tuned it on this specific corpus to improve its general reasoning capabilities before they even started teaching it to be a reward model.
It's like a finishing school for math?
It's like sending the model to a math boot camp, so it understands the syntax, the latex formatting, the general logic of derivations before you even start testing it.
That's smart. You don't want the model failing because it doesn't know how to format an integral. You want it to fail because it doesn't understand calculus.
Exactly. You have to control your variables.
Okay, so we have a super smart base model, prep schooled on MathMix. Now, let's go back to the two contenders. Outcome supervision versus process supervision. I want to make sure I have a crystal clear mental image of this because everything else sort of hinges on it. Outcome supervision, we call this an ORM, right? An outcome supervised reward model.
Correct. An ORM.
An ORM is basically a Scantron machine.
That is a very, very apt analogy.
It just looks at the bubble you filled in. If the answer is 42 and you bubbled 42, you get a point. It doesn't care if you guessed. It doesn't care if you used the wrong formula but got lucky.
Right. Maybe you made 2 negative errors that happen to cancel each other out.
Exactly. And it doesn't care if you scribbled, "I hate math" in the margins. It just asks, did you get the right answer? Yes or no?
Precisely. It provides a sparse binary signal at the very end of the generation. The big advantage of ORMs, of course, is that they are cheap. They're really easy to automate.
Because you have the answer key.
You have the answer key, which we do for the math data set. So you can train a model on millions of generated solutions without any human intervention. You just run a script. Does the output equal the target? Yes, no.
But the signal is noisy. That's the problem.
It's incredibly noisy.
Because of the credit assignment problem.
Right. And this is a fundamental concept in reinforcement learning. It goes way back. Imagine you are trying to teach a dog to fetch. You throw the ball, the dog runs out, it spins in a circle, it barks at a squirrel, picks up the ball, runs back, drops it, and sits. Then you say, "Good boy," and give it a treat.
The dog has no idea what you're rewarding.
Exactly. Does the dog think it got the treat because it fetched? Or because it spun in a circle? Or was it because it barked at the squirrel? That is the credit assignment problem. The learning signal gets smeared across the entire sequence of actions.
And in math, if I write a 10-page proof and get the final answer wrong, the ORM just says bad, thumbs down. It doesn't tell me where I went wrong. Maybe page 1 was brilliant and I just dropped a negative sign on page 9. The ORM punishes the whole 10 pages equally.
Exactly. It discourages the good reasoning along with the one bad error. It's a blunt instrument, a very blunt instrument.
Okay, so that's the ORM, Scantron. Now, process supervision, the PRM, or process supervised reward model, this is the strict professor.
It is the professor who reads every single line of your derivation with a red pen. The authors actually trained their generator model to output solutions in a specific format. It's new line delimited. So step 1, new line. Step 2, new line.
So it's forced to chunk its thought process.
Right. And the PRM assesses step 1, is this correct? Yes. Reward.
Yeah.
Step 2, is this correct? Yes. Reward. Step 3, wait, you divided by 0? Incorrect.
Yeah.
Punishment. Right there.
That sounds vastly superior for learning. I mean, it completely solves the credit assignment problem because the feedback is immediate and it's localized.
It does. It's a much cleaner signal. But there is a massive catch.
It's the cost.
The cost. You can't automate that easily. You can't just write a script to check if step 3 is valid logic. Logic is nuanced. You need humans.
And that is the bottleneck. Always. To build a PRM, you need a massive data set of step-by-step labels. And this paper is so impressive because they didn't just, hypothesize about it. They actually built that data set.
It did?
They released it as PRM 800K.
Which stands for 800,000 labels.
That is a staggering amount of boring, meticulous human labor.
It is 800,000 step-level labels across about 12,000 problems. It's one of the largest data sets of its kind ever released to the open research community. It was a huge contribution.
Let's talk about how they got those labels, because I imagine they didn't just grab random people off Mechanical Turk to grade calculus problems.
No, absolutely not. These were human data labelers who had to be screened for math proficiency. Their job was to look at a single step in a solution and assign one of three labels: positive, negative, or neutral.
Okay, positive and negative seem straightforward, correct or incorrect. But neutral is interesting. What is a neutral step in math? Isn't math supposed to be binary?
In a perfect world, yes.
Yeah.
But in the sort of messiness of LLM generation, neutral becomes this really important edge case. A neutral label means the step is ambiguous.
Ambiguous how?
Well, maybe it's not strictly wrong, but it's subtly misleading. Or maybe it's a valid statement like, the sun is a star. That is true, but completely unhelpful for solving the integral you're working on.
It's just fluff.
It's fluff or weird phrasing that might be correct, but is too hard for the labeler to verify quickly. It's a way to capture the fuzziness of language and logic that even creeps into mathematics.
So if the model says, let's assume X is 5 without any justification,
Right.
Is that neutral or negative?
That would likely be negative if there's no logical basis for it. But if the model says, look, rewrite this equation and just swaps the left and right sides, so y2x becomes 2xy, that's a good example of neutral. It's true, but didn't really move the needle.
Got it. Now, you mentioned the cost. 800,000 labels is a lot of human hours. Even with OpenAI's budget, you don't want to waste time. They used a specific trick to make this efficient, didn't they? Something called active learning.
This is, in my opinion, one of the most technical and brilliant parts of the methodology.
Right.
It's what makes this whole thing scalable. Think about it. If you just let GPT-4 generate solutions to math problems, maybe 80% of them might be correct.
Right. The base model is already pretty good.
And of the 20% that are wrong, many will be obviously trivially wrong, like 2 + 2 fish.
So if you show those to a human, you're paying a highly skilled person, $50 an hour to look at 2 + 2 fish and click the wrong button. That's a huge waste of money.
Exactly. It's low information density. You aren't teaching the model anything new that it doesn't already know. So they used an iterative process. They trained an initial sort of baby PRM on a small amount of data. Then they used that PRM to look at thousands of generated solutions and score them. And here's the clever part. They specifically hunted for what they call convincing wrong answer solutions.
Convincing wrong answer. Okay, break that down for me.
It means a solution where the model got the final answer wrong, but the current reward model thought the steps were good.
So these are the hallucinations. These are the wolves in sheep's clothing, the ones that sound plausible but are actually broken.
Exactly. These are the hard negatives. This is where the model is confident, the reward model is currently fooled, but the result is incorrect. This is precisely where the model's mental model of math diverges from reality. These are the most information-dense examples you can possibly show a human.
So they filter for these specific tricky cases, show those to the human labelers. The humans find the one specific step that tricked the model, they mark it negative, and then they retrain the PRM on that new hard-won piece of information.
It's like a teacher realizing the entire class has a specific misconception about, say, dividing by 0. You don't review addition again. You focus the entire next lesson on that one specific error.
You're optimizing for the gradients. You're finding the steepest part of the learning curve.
That's a perfect analogy. And it worked. By focusing on these hard negatives, they improved their data efficiency by 2.6x.
Oh.
That means they got the same performance with roughly 40% of the data they would have needed otherwise. That is the difference between this being a nice academic idea and a commercially viable strategy.
So they built the data set, they trained the PRM. Now we have a PRM that is essentially a highly specialized math critic. It doesn't solve problems itself, it just critiques solution.
That's right. It's a judge, not a contestant.
So now we get to the showdown. How do they actually test if the critic helps the writer? How do you measure the improvement?
They evaluate the models using a technique called best-of-n search. This is pretty standard in this field.
Right, but maybe just a quick refresher for the audience on best of n.
Sure. Instead of asking the model to generate one single answer and just hoping it's right, which is what we do when we use something like ChatGPT. You ask the model to generate n answers, say 100 different attempts at the very same problem.
So it's brainstorming.
It's brainstorming. Then you use your reward model, either the outcome scantron, the ORM, or the process professor, the PRM, to score all 100 of those solutions. The model then picks the one it thinks is the bad and presents that as its final answer.
So it's a filter. It's a quality control step.
It's a selector. And the metric is simple. How often does the chosen solution turn out to be actually correct?
And the numbers, what was the result?
The results are striking. The process supervised reward model, the PRM, solves 78.2% of a representative subset of the math test set. The outcome supervised model, the ORM, performs significantly worse.
A clear win.
A very clear win. But the most telling visual in the entire paper, and I wish the listeners could see this, is figure 3. It shows what they call the widening gap.
I'm looking at it right now. It's dramatic. It honestly looks like an alligator mouth opening up.
It does, doesn't it? On the x-axis, you have n, the number of solutions you generate. As you increase n, as you let the model brainstorm more and more ideas, the performance of the PRM just keeps going up. It gets better and better at finding the needle in the haystack.
Which makes sense. If you generate 1,000 solutions, at least one of them is likely to be right by chance. The PRM is good enough to find it.
Exactly. But now look at the ORM line. It just plateaus. In fact, if you go out far enough, an ORM can actually get worse as you give it more options to choose from.
Wait, hold on. How can looking at more solutions make it perform worse? That seems completely counterintuitive.
It's the spurious solution problem again.
Yeah.
As you generate more and more solutions, you generate more weird edge cases. You generate more hallucinations that accidentally land on the right answer.
Oh, right. The broken clock is right twice a day effect.
Yes. But if you have 1,000 broken clocks, a lot of them look like they're telling the right time at any given moment. The ORM only checks the final answer. So if the model guesses the right number but used a magic spell or completely flawed logic to get there, the ORM says, great job, this is the best solution.
It selects for luck.
It selects for luck, and you could argue for certain types of deception. The PRM sees the magic spell, sees the bad logic, marks it as a negative step, and immediately discards that solution. The ORM gets fooled by the noise. The PRM filters the noise.
That is such a profound difference. It means the ORM is fundamentally capped. It's capped by its inability to distinguish luck from skill. It hits a glass ceiling.
A glass ceiling is a great way to put it. And this brings us right back to that alignment tax idea. The PRM is safer because it catches the magic spell logic. It catches the unaligned reasoning. And because it catches that, it picks the actually correct solution more often. Safety equals capability.
Okay, now I have to play devil's advocate here, or maybe just skeptical peer reviewer number 2. Is it possible that the PRM just won because it had more data? Or, because GPT-4 is just so big that it can simulate a human grader perfectly and smaller models couldn't?
A very fair question.
Yeah.
And the authors anticipated that. They ran what they call a small-scale ablation study to control for exactly that. They realized they couldn't just create infinite human data for every test condition, so they used synthetic supervision.
Using the big model to teach the small model.
Yes, exactly. They used their big GPT-4 PRM to act as the human labeler for a set of much smaller base models, like models a tenth of the size. This allowed them to control the variables perfectly. They could give a small model exactly the same amount of training data for outcome supervision versus process supervision.
So it's a true apples-to-apples comparison of the method, not just the resources thrown at it.
Exactly. And the result? Process supervision still won, and won decisively. Even when you control for the amount of data, verifying the steps is simply a more efficient way for a model to learn than verifying the final outcome.
It just makes intuitive sense. It goes back to the dog fetching the ball. If you use a clicker and click exactly when the dog grabs the ball, it learns in 10 minutes. If you just give it a treat 5 minutes later back in the house, it might never learn.
The PRM is the clicker. It points a laser at step 4 and says, this specific derivation is wrong. The model learns exactly what it needs to fix. It's a much sharper, much cleaner learning signal.
This also touches on something that we care about so deeply in alignment, which is interpretability.
Oh, absolutely. An ORM is a black box. It gives you a score, a single number, but you don't really know why. A PRM gives you a map. It shows you exactly where the model thinks the logic holds and where it breaks down. You can literally visualize the thought process.
The heat maps.
Yes, in the paper, they show these heat maps. Green steps for good, red steps for bad. You can follow along.
I loved those visuals in the appendix. There was one example, I think it was really complicated polynomial factorization.
The Sophie-Germain identity problem.
Yes, that's the one. A really nasty factorization. Most humans would not spot the trick. And the model pulled out this obscure identity, the Sophie-Germain identity, which is a very non-obvious step. And the PRM flagged it as green. It recognized a brilliant creative move.
That's significant.
Yes.
It's really significant because it shows the PRM isn't just looking for standard textbook steps that it's memorized. It can recognize creative, valid reasoning, even if the logic is unusual.
But they were honest. They also showed the failures.
They did. There was a probability problem where the model made a simple counting error. It forgot that Bob had 2 choices instead of 1 or something like that. The PRM missed that one. It was a false positive. It thought the logic was fine when it wasn't.
Why do you think it missed it?
Because counting is notoriously hard for LLMs, and therefore checking counting is also hard for LLMs. The step looked linguistically plausible. The structure of the sentence was correct, even though the number was wrong.
But then there was another one, a class average problem, where the model messed up the distributive property, something basic like 2x plus 5 equals 2x plus 5, and the PRM turned that step bright red immediately.
So it's not perfect. We have to be clear. It still misses things. But it encourages what the safety community calls human-endorsed chains of thought. It forces the model to reason in a way that humans can follow and approve of.
It reduces the risk of the model learning to game the metric.
Exactly. In AI safety, reward hacking, or gaming the metric, is one of the huge existential fears. If you tell an AI minimize cancer rates, and it decides the best way to do that is to kill all humans, technically cancer rates go to 0.
That's the ultimate outcome supervision failure. The outcome is achieved, but the process is catastrophic.
Right. But if you use process supervision, you check the steps. Step 1, acquire large amounts of poison. Red flag, stop, halt program.
This feels like it has implications way, way beyond math problems. If we can verify steps in math, can we verify steps in coding?
In legal reasoning, for medical diagnosis. That is the big hope. That's the billion-dollar question. The authors explicitly check for owed generalization. That's out-of-distribution testing. They didn't just test it on more problems from the math dataset. They threw completely different exams at it.
Like what?
AP Physics, AP Calculus, and Chemistry exams.
What happened?
The PRM still outperformed the ORM and other methods like majority voting. It generalized to new STEM topics that it hadn't been explicitly fine-tuned on. This suggests that the skill of verifying a logical step is at least somewhat transferable.
Logic is logic.
Logic is logic, whether it's in a vector space or a chemical equation.
That is incredibly promising. It suggests we aren't just overfitting to a specific test bank of math problems. We are actually teaching it how to think, or at least how to check its own thinking.
I think that's the right way to frame it. However, we should be careful and note the limitations. The authors themselves are very honest about this. The data set is still very math heavy, very STEM focused. We don't know for sure if this applies to, say, writing a creative essay or making a subtle moral judgment.
That's a great point. In math, a step is generally valid or invalid. There is a ground truth. In a geopolitical analysis, a step might be valid but biased or valid but completely irrelevant.
Exactly. Defining neutral steps in a moral argument is much, much harder, and the cost is still a factor. Even with active learning, human expertise is expensive. To scale this to every domain of human knowledge, law, medicine, engineering, philosophy would be a monumental undertaking.
But the release of PRM 800K, the dataset itself, seems like a deliberate move to lower that barrier, doesn't it? They're basically giving the community the fuel to build their own verifiers.
It is a massive gift to the field.
Yeah.
It really is. It allows university researchers and smaller labs who don't have OpenAI's budget to experiment with these alignment techniques. It effectively democratizes the research into process supervision.
So if we zoom out, we started this deep dive talking about the fear of hallucination, of the confident idiot. Does this paper solve it?
Solve is a very strong word. I don't think anything solves hallucination completely yet, but it provides a robust methodology for mitigating it in a huge way. It proves that we don't have to choose between a smart model and a verified model. It shifts the paradigm from train big, hope for the best, to train big, verify small.
Verify small. I like that. It's verifying the atomic units of thought.
And it suggests that the future of AI alignment might look a lot like teaching. Not just grading the final exam, but sitting down with a student, checking their homework line by line and saying, no, look, your logic broke right here. Fix this specific thing.
And if we can do that, we can build systems that aren't just powerful black boxes, but transparent partners. Systems we can actually begin to trust because we can see the work.
Precisely. That's the goal.
Okay, we have covered the methodology, the results, the widening gap, the credit assignment problem, and the beautiful concept of the negative alignment tax. This is typically where we would wrap up the facts. But on Talk Tensors, we like to take those gradients and extrapolate them a bit.
It is time for the novel notions.
And time for the disclaimer. The following segment is for entertainment purposes only. These are speculative, unproven, and potentially outlandish ideas inspired by the paper we just discussed. Please do not try to build these at home unless you have a GPU cluster the size of a small country.
And even then, you should probably proceed with caution.
Novel notion number 1. We've talked a lot about math, but let's talk about the structure of society itself. I'm calling this the legislative PRM, or process-based law.
Ooh, okay, go on.
Right now, we judge laws largely by outcome supervision. Did the GDP go up? Did crime go down? Did the bill pass? It's a binary outcome, and usually the feedback loop is years long. It is the ultimate noisy signal.
And credit assignment is absolutely impossible. You pass a 1,000-page omnibus bill, the economy crashes 2 years later, and nobody knows which clause or which interaction caused it.
Exactly. So here's the pitch. We trade a PRM not on math, but on legal logic, constitutional law, and ethics. We use a panel of legal scholars, economists, and ethicists to label the steps of a law, the individual clauses, and their derived logical consequences.
So you are verifying the derivation of the law itself, not the outcome.
Yes. The generator model writes the bill. The legislative PRM checks every single clause. Is this clause logically consistent with the Constitution? Positive green. Does this clause create a hidden loophole for a specific corporation? Negative flag. Does this derivation of policy actually lead to the stated goal, or is it a complete non sequitur?
This is fascinating because you're forcing it to enforce procedural justice over consequentialist justice.
Correct. The AI would literally refuse to write a law that contains a negative step, a logical fallacy, or a hidden unethical loophole, even if it predicts the law would be popular or pass a vote. It forces the legislative process to be honest, step by step.
You're essentially building a compiler for law, a linter that throws a syntax error if you try to sneak in corruption. Error on line 452, logical inconsistency detected between tax code amendment and existing environmental protection mandate.
Exactly. No more 1,000-page omnibus bills where nobody actually knows what's in them. The PRM demands that the logic compiles cleanly.
I like it. It's incredibly high stakes, but it applies that negative alignment tax concept to governance. The safer law, the one that is logically sound, is also the more capable law.
All right, notion number 2. This one is a bit more sci-fi. I call it recursive Socratic debugging.
Socratic, as in Socrates, asking questions.
Exactly. We talked about the neutral label in the data set. Currently, the paper says they just treat neutral as either positive or negative based on some threshold. It feels like a bit of a waste of a nuanced signal.
It is. You're just throwing away ambiguity.
Right. So my proposal is this. We train a model where a neutral score doesn't just mean move on. It triggers a halt command. The model literally stops its own thinking process.
It freezes the inference.
It freezes. And then it spawns a sub-agent, a little debugger agent.
Yep.
And that sub-agent turns to the human user, or maybe a more powerful super verifier model, and it asks a clarifying question. It says, I am about to make an assumption here. This step feels neutral. It's ambiguous. Is this assumption valid?
So instead of just hallucinating a fact to bridge a logical gap, it explicitly admits its own ignorance.
It effectively operationalizes the phrase, I don't know. It moves us from a chain of thought to a tree of verification. The model cannot proceed past its own uncertainty without getting permission.
This would completely solve the hallucination problem for high-stakes engineering or science. If you are designing a bridge, you don't want the AI to guess the tensile strength of a new material. You want it to stop and ask, the data is ambiguous here. Are we assuming standard steel or this new titanium alloy?
Exactly. It turns the AI from an oracle that pretends to know everything into a Socratic partner that debugs its own uncertainty recursively. The final output you get is not just the answer, but a full transcript of the questions the model had to ask to get there.
That is a very powerful shift. It changes the user interface of AI entirely. It becomes a dialogue of verification, not a monologue of generation.
And that, my friends, is why we verify step by step. Because whether it's a math problem in the law or a bridge, the process matters just as much as the outcome.
Perhaps even more.
A huge thank you to everyone for tuning in to this deep dive on Talk Tensors. Please check the show notes for the link to the paper. Let's verify step by step and the PRM 800K dataset if you want to geek out on the data yourself.
And remember, in a world of black boxes, always show your work.
Keep your gradient steady and your loss low. We'll see you next time.